Thank you for the introduction. So I'm from Netflix. I'm senior research scientist at Netflix. I'm also working on Spark in my free time as a Spark committer. So today I'm gonna talk about how Netflix build our recommendation using the machine learning pipeline with Spark by consuming the house of data. You know, Netflix is known for house of data. So at Netflix, we want to have a day that when anyone, they sit down, turn on the TV, start to watch Netflix, and they can see absolute best content they want to watch at the right moment. And we are still not there yet, but it set a vision for us to improve our machine learning algorithm to spend our service. So where do we exactly use machine learning? We use it everywhere. As you guys can see in the page, you know, the video in the row are personalized for different persons. And also how do we compose the page by have different type of row. It can be a trending now, continuous watching, or like a romance, or whatever. How do we compose the page? It's also a machine learning algorithm. And then we depend on your mood or whether you want to continue to watch on something you have watched yesterday or whatever. By promoting some row up, there is an algorithm. And also, how do we pick up the image on the title is also a machine learning algorithm. So we use machine learning everywhere in our product, and that's our core business values. So over like 80% of the traffic of the watch at Netflix come from like one sort of like a recommendation systems. And our recommendation system is driven by machine learning algorithm. We don't manually like put into like, oh, those are type of content you're probably gonna watch. We learn it from like your past behavior and try to predict what you want to watch next. And that's how we can scale it, like, you know, to like more users. As you guys know, 2016 there's a really big news. There was a really big news for us. So we announced that we're gonna go global. Netflix basically everywhere. And right now we have more than like 93 million of the members, and our service is available in more than like 190 countries. And the challenge is that when we go global, we have more traffic, more users, and each user has different like preference they have different language, and they have in different countries, and people tend to like, you know, watch something like a local, or they tend to watch something like a personalized in their particular countries. So how can we build an algorithm, which is the global algorithm? We are not going to build algorithm for like each country. We want to build a global algorithm so we can easily, you know, serve all the members. And also for each country, we have different catalog. So how can we build an algorithm for this kind of like environment? So that's a really big challenge for us. And because of that, we constantly doing like, you know, innovation, doing research at Netflix, like people at MIT, Harvard, you know, they are working really hard. We are also working really hard, reading papers, try different type of experiment, and see which idea can work or not. And we do it by A/B test at Netflix. And pretty much every member at Netflix is pretty much in one kind of like A/B test experience right now. We have a lot of concurrent A/B tests running at Netflix, and pretty much everyone is in one of the A/B test experience. So from like how we change the UI, how we like, you know, change the algorithm, those like we go through the whole A/B test cycle to decide that, oh, whether we want to roll into production or not. Okay, so how do we make our algorithm better to realize our visions? So we follow two-step like approach. So first of all, we try to like, an idea using like a historical data. So we have lots of historical data. We try an idea and try to build models. And then we're gonna see like offline metrics. And if the offline metrics work pretty well, we will probably try it out in the online A/B test and see if it actually help our like a core metrics, like the retention or streaming hour, member engagement, or user satisfaction. So lots of time the offline metrics can be like not correlated to like the online metrics, because offline metrics is looking for like NDCG, recall, this kind of ranking metrics. But lots of time it's not actually correlated to online. So we still need to do the online A/B test to try it out and see how it works. And the other challenging is that once we try an idea and it's worked really well in the online metrics, we want to bring it into production as soon as possible, or like roll it out as soon as possible. Or the A/B test itself is kind of like a production, because there are lots of users in the A/B test cells. So how can we prototype an idea and quickly bring into the production to try it out is a key challenging for the machine learning infrastructure, which we are doing at Netflix. So let's talk about like the high-level overview of how we build machine learning models. So first of all, we collect the data. They can be like the user watching behavior, like user watching viewing history, and then we computer features. So can be, I'm going to talk about that in detail. So we computer features, and then we can train some models. Can be like single machine, like a multi-threaded model, or like some distributed algorithm. So we train a model, and we pick up the best model by doing the validation, and then we do a computer final metrics by using the test data set. And if the model doesn't perform well, we will go back and then try to learn from the experience and try to improve it. So it's an iterative process. And whenever we see like a good offline metrics, we will bring it into online and then test it out with the real user and see whether they move like core business metrics. So in order to innovate faster and more efficient within the big machine learning team, we standardize our data format within the ranking problems. And the reason why we want to do it is that once we have a standardized data format, you can easily build some tools, libraries, or algorithms using the same data format, which means we can innovate faster, and everything is kind of like Lego. You can plug and play. So we have a shared data format for the ranking problems. And I'm going to talk about that soon. So for the ranking problems, you can think about that you have a context. So context is a minimal building block for ranking problems. So items are the element to be ranked within a context. So to be more concrete, for example, when people do like a learning to rank approach to build rankers, the context can be like a user in a given country. So basically, you want to build a ranking for a user within a country. Or maybe can be a user within a country, a given device, because different devices can have different like recommendations. So you can have different mode with different devices. And the items will be all the video available for that particular context. And for the search example, there can be a query for a given user. So the context will be a query for a given user. And then the video will be, the items will be the candidate video within that query. And then and for the users. So we want to build a supervised model such that we can rank those items within the context. And label will be for us to build the supervised learning model. So I'm going to talk about that later. Okay, so here is our share format in as a Netflix. So we call it like a DMC12 or DeLorean format. DeLorean means time machine, so we are trying to predict something tomorrow for you, or like, based on the historical data. So as you can see, the top two is a nested structure. So the top two is like, the profile ID in a given country. The context can be more like a device or whatever. Those can be part of the context, but I'm showing here as an example. And then you can see like, you have a bunch of video, which is in the elements. Okay, and then you can see also we have features for each videos. And then in this case, you can build a model for that. Okay, so why do we use the nested structures? So we always can actually flatten it out, but the problem is that when you want to compute a rank or doing the ranking, you want to group all the items within like the same context together. And that will involve some kind of like shuffling in Spark. You need to group by key. Key will be the context. And that is relatively expensive. So we group them together as a nested like a structure. So when you do the ranking, it's already within the same row. So basically it can avoid like a huge shuffling. And that is pretty efficient. And the feature we have can be derived from some like a business logic, or it can be the output of the other models. So finally, we have the data. Normally, we have the data persist in Hive in Parquet format, such that later on we can examine the data and see like, whether we can build using different like learning to rank models or like doing some debugging. So we use Parquet and Hive. And we use like, the ensemble method to build a learning to rank model to build a final output. Okay, so I'm going to talk about Transformer. I just know that yesterday. So if you are a fan of the Transformer movie, you're going to know Spark is the soul of the Transformer. So, okay, so what is a Transformer in Spark ML? So Transformer can have some certain logic inside, and then it can take input data frame, and then transform it to another like output data frame in a lazy way. So it's a lazy transformations. And it's ideal for like training multiple transformer together, and the computation will only be triggered in the final stage when you perform an action. And all the intermediate result will not split into disk, of course. So it's kind of useful. And we extended, at Netflix, we extended and make it something called item transformer. So item transformer will take our DeLorean like data format, like DMC12 data format, with some contextual information, which is the context information. And then we can transform the data frame in the item level. So to be concrete, I'm gonna give you a couple examples about that. Okay, so why do we use data frame? So we found that it's pretty fast. It has all kind of optimization built in right now, and like a predict push down or a lot of them. And then with transformer, you can do upfront like a schema verification, which is pretty nice. So you won't run into like exceptional errors, like while you are. So you're gonna have the exceptional error in a really early on, instead of like when you start a job, it's fail. So that's pretty good, cool. And we find like a 4 times speed up when we put our previous feature generation code from RDD into data frame like ecosystems, which is pretty nice. Okay, so one of the examples is like a negative generator. For example, for all the data we have, we only have what user watch. Like we don't know whether user doesn't, what video user doesn't like. So we need for the supervised learning problem, we need to create some negative samples for users. And it's so-called like negative generation. So this can be like based on certain model, or this can be based on some business logic to create negative. So you only have positive, but we want to create negative for the supervised learning. So how do we do it? We have a bunch of different ways to do it in-house, and we want to standardize it and share the logic so people can quickly try it out. So that can be item transformer. So based on the contextual information, like a user in a given country, you can do an item level transformation. So basically, the input from the left-hand side only have positive, which means you only have label, which is positive. But the output on the right-hand side will having the output containing negative. So basically, we have a transformer creating the negative. So that's one of the use case we have for the transformer. And also for the feature generation, it can take the input data, which is the output from the previous slide, and we compute the features. So we actually just append the features into the output data frames. So it's kind of like transform. It's a bunch of transformation to prepare the features. So how does the code look like? The code actually looks like this to create the features. So we need to take the data. So we have something like tagging transformer. It's take the data randomly into test data set, training data set, and validation data set. And then we need to do some kind of country tenure stratification, stratified sampling, because we don't want a certain country overrepresent the data. So we have something like that. So it can be some kind of module, a transformer, which can be shared across different teams, and people can try it out. And then we finally do negative transformer and doing the feature generation. So you can simply using those simple code to create the features for the supervised problem we have at Netflix. So it's pretty nice. Okay, so how do we do training? So not actually all the algorithms are suitable to be implemented in MapReduce. For example, like SGD is not an ideal candidate in MapReduce framework because MapReduce is doing the force synchronization. So for SGD, people want to do parameter server, for example, or building a tree is pretty hard to do it in MapReduce. Not really efficient. So the cost of the communication for the MapReduce framework can be really high for those kind of algorithms. So some of our in-house algorithm is implemented in a single machine and then multi-threading implementation. So we're gonna deploy it with a really big machine and then run it with hundreds of code in one machine or a really big machine. So how can we do it inside Spark? Because it doesn't fit into the Spark paradise. So what we do is for this kind of algorithm, what we do is we use Spark to instruct the executors to do the parameter searching. And in this case, each executor or each machine will only run one Spark task with certain parameters. And then we're gonna launch many of them to do the parameter searching. And in this case, the data structure is kind of different because data frame or RDD is a distributed data set. And right now you want to have all the data in each executor. So how do we do it? So we try broadcast first. And broadcast doesn't work well with the big data set. It's going to fail because there's some limitation on broadcast. So we build a framework such that we can save the data into HDFS. And then in the executor side, we are streaming the data from the HDFS into the channel, into the multi-threading channel, so we can train a model in the executors. And it's actually managed by Spark. So when you do final reduce, we bring in back all the models, so we can compute the metrics in a distributed way. So that's how we do it for the multi-threading model training. And for the distributed model training, we also use some of the Spark ML algorithm. And because of that, we try to keep the interface similar, such that we can easily plug and play, trying out different algorithms. So we have the interface quite similar. And once we have the models, how do we do the scoring and ranking? So for us, the scoring is actually score is actually the return of the channel. So, so it's a model actually. So what we do is that we implement score as a transformer as well. So if you apply the score on the DeLorean DMC12 data format, it's actually append, it's actually computer score. Score can be probability or whatever. So it can compute a score based on the features, and we append a new column in the data frame. So we get a score as an output data frame. And then together with score and labels and the video ID, we can compute like the normal like ranking metrics, like MNRR or NDCG or recall. So that's how we build a whole like a machine learning PiPI framework. And we learned some lessons from like building this kind of infrastructure. So the good thing is that by using the PiPI framework, we are able to build each like a building block with a really modular way. And then because of modularity, it's really easy for us to write like a unit test to cover like the potential bug can be happen. And because of like it's modular, so we can easily plug and play. Like different people can implement different module, and we can actually try it out, like different kind of combination. And because of the shared library using this and like a modular, and then using this and like a data format, we often like doing a lot of prototyping or experiment in notebook, because I mean the whole like structure doesn't depend on like I/O, doesn't couple with I/O directly. Everything is like done by like a data frame, the input data frame, output data frame. So you can like load the data from Hive fairly easy, and then using this kind of PiPI architecture to like to build some prototyping for the experiment. And also the interface is really easy for a developer or like a scientist to extend. So they can build their own algorithm, build their own sampling, build their own like, different kind of feature generation, because it's kind of like all like, extending this interface. So people can customize it, implement their own idea, and then commit it into the central repository, and the other people can also try it out. So that's pretty cool. And the whole thing, we have the schema verification. So in each step, like a schema is being verified, so you don't run into some kind of like a runtime exception too much. And we built our own way to serialize the whole model and deploy it into production. So I'm going to talk about the reason why we want to do it. We need to do it. So the problem for using this kind of framework is that the whole like pipeline idea is strongly coupled with Spark platform. So in the production, it's impossible to bring the whole Spark environment in. It's like a purely like really clean Java application. So so in this case, we need to build like our own like scoring engine for the production, and then write a translator between two of them, which is kind of like extra work. And also like, the matrix evaluator at Spark doesn't support like doing the ranking, doing computing the matrix for multiple model in one pass. So it's only allow you to compute like a matrix like for one model as a one pass of the data. So for example, we are building like a 10 model, and then we are computing 20 different kind of metrics. Then you need to go through the data like 200 times, which is pretty expensive. So we need to customize this part of the code in order to do everything by loading data once, and then compute all the information we need. So those are the issues we saw in Spark, and we also constantly help out to like improve it. Yeah. So yeah, that's it. So any question? Sure.
I was just curious if you could talk a little bit about how you did use that in production, some of the challenges you faced there.
How do we deploy the model in production? So yeah, So we built a common library at Netflix called ArgoCom, and those code are for like production and offline experiment usage. So those code contain like how production can like score a model. So it has its own score, which doesn't depend on Spark. And then we wrap it into our PiPI framework. And then those like ArgoCom also contain a logic how do we compute the features from like the microservice system, like viewing history or like the rating, and then those design code can be deployed in production and offline because those are pure Java app, so they don't have any dependency on any special platform. So that's how we like doing the deployment in production. Yeah, good question.
Hey, so my question's a little weirdly technical, but you said that there's problems with broadcasting large amounts of data, and therefore you'd write to HDFS and then stream off there. I've actually encountered the same sort of issue and sort of hacked together something very similar. Have you considered like pushing your changes or something into Spark? Because it'd be nice if there was like an actual implementation.
Yeah, that's a good idea. So once we have like a more mature like development, some of the stuff can be merged back to open source community. Yeah.
Hi there. Can you show like how your environment look like kind of Hadoop ecosystem? If you have some kind of diagram here.
Can you like
means how your data structure and then analytics look like if you means in your production, how you implemented your solutions?
Oh, so our production system doesn't depend on the Spark or Hadoop environment. So it has its own environment, which doesn't depend on the big data platform. So that's why, as I mentioned, we have a shared common code base between production and the offline model training to like do this in logic. But they are because Netflix is doing a microservice architecture. So for them, they are calling the live system to compute the features. But for us, we are using a feature in Hive to compute the features. Yeah, but the logic is shared by common code base.
Can you comment about the linear algebra? How do you include it in the pipeline, Spark ML pipelines? Because most of the linear algebra in Spark right now is RDD based. It like uses the BLAS library for Fortran. So in my case, I often have to go back and forth between data frame and RDD. Can you comment on some best practices for that?
Sure.
Another question, if you can, you mentioned the hyperparameter search. I know there is the grid search in Spark, and do you know any solutions for random search?
Okay, good question. Yeah, so for the first question, in Spark 2.0, we separate our like linear algebra from like a Spark ML library out into like a standalone jar, so which allow us to use like in production and also in the offline Spark experiment. And also normally like loads like a Spark, like a vector or whatever, we have a user-defined type such that you are allowed to use them in the Spark SQL environment. So you are allowed to write UDF about it. Oh, okay. Maybe we can sync up this offline. And then the second question you were asking is about, oh yeah, random. Yeah, so we have a similar implementation in-house. It's not using Spark 1. Yeah.
Can you talk about lessons learned when you bring on a new country? Do you consider features of the model you like and content's coming and going? Can you give us some insight on how you dealt with that?
Oh, good question. You can join us and you're gonna know more information. Yeah, we have opening now. Cool.
Okay, last question.
So looks like you have a supervised model, right, for every subscriber in the system. So how do we model the negatives, right? So because you don't get any feedback on them. So what is the concept of? So is it like a multi-value kind of a
it's also a good question. There are a couple ways we are doing that in-house, and there is kind of like, you can join us to know.
Thanks, everybody. Next session is going to be a presentation by Verizon on using timestamps and machine learning. Thank you.